Hello, and today we'll be working on a homework problem here dealing with material balances, including dynamics and control. So, as you can see on the screen here, I have pulled up the actual problem description so that you can sort of see it. And what I have here that is sort of covering my face is my phone. And the reason I have it set up this way is because instead of doing it on the whiteboard, I want to do it on a piece of paper, and my phone here is capturing that video of me working on the paper alongside of me talking what I have here. So sort of double live action. So how about we get started with the actual problem? So as we start reading this, we see that there's 3 tanks with cross-sectional areas of those values, and they're all interconnected at their bottoms. And so what I want to do initially here is to sort of draw this out. And because I have ran into this problem before, I know uh, that the third tank, the one on the very far right, the way I have it drawn now, will be flowing out to wherever empty space or wherever this, if this is a real life situation, wherever they want it to flow to. So they have these pipes being connected at the bottoms here. And I will label this first tank 1, 2, and then 3. All right, and then after that, we are also given their initial fluid heights. So we are given their initial parameters, right, that we'll need to simulate in order to simulate in Python later in part 2. So let's write those down. We have the initial height of the first tank, which is 0.5 meters. The initial height of the second tank, which is 1 meter. And the initial height of the third tank, which is 2 meters. I'll write that in here. Of course, I shouldn't forget the cross-sectional areas. Those parameters were also given, so I'll write those here, which they all have the same values as the heights. All right, so let's continue on with the description here. So we are also given that the magnitude of the flow between tanks is proportional to the square root of the difference in fluid heights between pairs of tanks. All right, so that's a lot. So this is related to a certain equation dealing with the flow of the output. And that general equation is this. Q, which represents flow, um, is equal to some proportionality constant times the height of the fluid level inside the tank to the 1/2 power. And it says that in there, right? The magnitude of the flow, right, is proportional, and we need proportionality constant here to the square root of the difference of heights. So that's where these tanks sort of interact, right? They're connected at the bottoms and flow goes in and out of them. And so we need to sort of tailor this now to the individual tanks. And so I will do that in a bit. Let's just keep on reading through the problem here. And so we are given that the constant, proportionality constant, the alpha value from 1 to 2, and then the alpha value from 2 to 3 is equal to both 0.1. And then we're given that tank 3 drains to the surrounding at a height of 0 with the same proportionality constant. So we know the alpha of 3 is also 0.1. And we also know that tank 3 has the general version of this equation for its outward flow, because that outward flow is not interacting with any other tank. So we'll keep that in mind here. And then we have this control. And for that, using the simplest form of control, proportional control, the flow into the second tank. So now we know, we can update our drawing here, that the whatever input that we're going in, that we're putting into these tanks is going into the second tank, right? And we want to make sure that the set point is for the third tank. So we have a set point for the third tank. So I'll put that here. We have a H3 set point, and that's for 4 meters. And the equation that will relate the flow in with the set point is stated in the question description here, where it's set equal. So the flow in was set equal to a proportionality constant, Kc, multiplied by the difference of the set point and the actual height of the third tank. And so as these levels adjust, Qin will also be adjusted, right? And then we also know that Kc is equal to 0.1. All right, and that's basically about all that we get from the description. So we can now start working on part 1 here, which is to derive the differential equations to solve the fluid levels in the 3 tanks. So, as we know, these tanks are not 2D, right? They are 3-dimensional. And so the thing that's actually moving around in it is that's changing, right? That's changing is the volume. But what you might notice is that we are given cross-sectional areas. And it can sort of be assumed from the description that these cross-sectional areas are constant, right? So if the cross-sectional areas are constant, well, we'll see where that leads here. If I write the differential equation, the change of the volume, right, and volume is the cross-sectional area times the height, and I'll write it for the first tank here, with time, right? And like I said earlier, with the cross-sectional area being constant, that isn't changing. So we can sort of pull it out. So instead of this, I don't know if you can see it here. Move my paper around. So instead of writing it this way, we can write it this way, where it is just the height that is changing with time. And so with these material balance questions, right, we have to think of an equation for it, right? What is the first equation that comes into mind? Well, it's the accumulation, right? But from this problem, which is a rather simple problem, there is no reaction going on, no mass going in or out. The only thing that's happening with these tanks is that there's flow in and that there's flow out. And so the way our equations will be set up will simply be that, flow in and out. And so we have our equation here in terms of flow in and out, and this is in terms of the first tank. This flow in, general flow in, won't apply to it. And so we are working with just this equation here. So what is happening inside tank 1? Well, we're given that the flow, and I'll write this separately here. We are given that the flow of, so there's a pipe from 1 to 2. So the flow will be from 1 to 2. And that will depend on that proportionality constant, right, for 1 to 2. And from the problem description, they say it's the square root of the difference of the heights, right? And so how does that work? Well, thinking about it logically, I just realized you might not have seen some of that pointing I did. But anyway, if the fluid height, let's say, suppose, is higher in 1 than it is to 2, flow will happen from 1 to 2, right? So let's say I want it that way. I want my flow to be positive when 1 is higher than 2. So I'll write it that way. But obviously, if we reverse that scenario and the height in 2 is larger than the height in 1, this value here will become negative, and you can't square root a negative, especially when you're applying it to real life situations, right? This isn't just theoretical math. And so how do we sort of circumvent that problem? And so what we could do is put an absolute value in here. And then a new problem arises, right? We solve the problem now, another problem comes up. How would this be able to model flow going in from 2 to 1? Since I have set it so that a positive value is flow from 1 to 2, how could we sort of now model how flow from 2 to 1? And there's an easy solution to that. We can sort of insert a value that we multiply throughout where it denotes the sign of h1 minus h2. So if this were to return a positive value, right, and I wanted positive to be flow from 1 to 2, we would get the magnitude from this and then the signage from this, right? So that would be positive value. So it would be from 1 to 2. If this were to come as a negative value, we would get the negative sign and then the magnitude from this absolute value here. And then that would be able to correctly model the flow from 2 to 1. And so we have our equation here for the flow of 1 to 2 being the sine of h1. Make sure you guys can see this. h2, alpha 1, 2, and then it's the absolute value of h1 minus h2 here to the square root. And now we have that for q1, 2. And now we can sort of put it into our differential equation. But we have to think about it real quick, all right, just to make sure it's correct. Sorry for the cut there. There were some issues. They've been taken care of. Back to the content though. So we had just finished working out the equation for the flow from 1 to 2, which is the only thing that is occurring within tank 1, right? That is the only flow that is happening within tank 1. And so we have made it so that the positive value of the flow from 1 to 2 is when the height of tank 1, the fluid level in tank 1, is higher than 2. And in doing so, that means when Q1, 2 is positive, the height level in tank 1 is going down because the flow is happening from 1 to 2, correct? And so what is changing here is the height level. It's going down, right? So we have to make sure our flow here, our Q1, 2, at least in terms of the volume, is negative, right? So that will be our equation for tank 1 being done. And so it isn't too much different for tank 2 here, at least in terms of the flow equations. So what is happening? So we've already done the flow from Q1 to 2. So we have this left portion complete. So now we have this, which is simply a flat value. Q in is a flat value. And we now need to focus on this piping, the 2 to 3. And it's not too different in terms of explanation and sort of creating the equation, working it out. It is actually the exact same as the flow from 1 to 2. And so we can write it that way. Said obviously you'll use the values of the respective tanks. Right? And so we have that done now. And now we can model start a second sheet here. Our differential equation for the dynamics within tank 2. And so just like the first tank, since the cross-sectional area is constant, the only thing that is changing with time here, I just realized I've been writing initial height. My bad. To clarify, from now on, I'll change it on my other sheet here too. Is not the initial height that's changing, correct? I've been saying, I'm pretty confident I've only been saying height that's been changing, right? It's only the height that's been changing with time here. And so what are the dynamics within this tank too? So we know from earlier, if Q12 is positive, that means flow is going into tank 2. It means the volume will be going up. And so that has to be a positive value. Q in is a straight up just stuff going in, right? Can't be sucked up or anything. So that is also a positive value. And with flow from 2 to 3, we have made it so that the positive, if 2 is bigger than 3, flow will go from 2 to 3. And with doing that, if flow goes from 2 to 3, the volume will go down, the height will go down, right? And so we have to assign this a negative value to represent the decrease in height. And we have that done now. And we can move on to the simplest of the tanks, that being the third tank, right? So we can sort of set up the differential equation here. So the height in the third tank changes with time. We have the flow from 2 to 3, and then the flow outwards. There is no flow can't get back in. It is simply flowing out. And with that, we can use the general equation that we have set up earlier, which is this one right here. And that will be, you just replace the generic height here with the height for 3. And so to see what that looks like, Q3, the flow coming out of 3, is the proportionality constant of 3 to the height of 3 to the 1/2. And so since that would decrease the height inside tank 3, we assign it a negative value. And there we have that. And so I will also, in terms of the question for part 1 here, derive the differential equations to solve the fluid levels in the 3 tanks. This would sort of complete it. This one, and this one. But you notice I haven't done anything with the control, and that isn't too hard either. This will sort of play into part 2 here, and just to have the equation sort of figured out already, I will do it here as well. So we have the equation for it that we found out earlier. Q in equals Kc times the difference between the set point and that. And actually, that is it for the equation for that. And with that being done, we have successfully completed part 1. So we will move on to part 2 here, where we simulate the dynamics of this controlled 3-tank system by solving the differential equations in part 1 using a specific method that is in Python here. So I will see you guys in the next video.